Can anybody hear me now?
Yes.
Yes.
Sorry about the glitch. Sorry about the technological glitch. All right, here we go. All right, so let's dive right into 2.5 before something else happens. All right, so this is applications of linear functions, ladies and gentlemen. So far, we've seen a couple different forms for linear equations. We've seen that if a linear equation is in this form, it's in what form? Anybody remember the name of the form here? If a linear function or linear equation is in this form, it's said to be in standard form. And oftentimes we like to solve the equation for y to put it into this very special form called what form? It was a slope-intercept form. Ladies and gentlemen, there's another form for linear equation that's right here. It's called point-slope form. Point. It's called point because they give you a point on a line, which is x sub 1, y sub 1. It can be read right off from the equation. And it's called slope form. Point-slope form because they also give you the slope m. That's called point-slope form. Trust you me when I say that you can always navigate back and forth between any one of these forms just by applying algebra to the equation. So you can always go from point slope form to slope intercept form and back to standard form, et cetera, et cetera. You can always go from standard form back to slope intercept form. All right. Well, do you really need to use point slope form? Well, probably not, because you could probably get away with using your slope intercept form to derive the equation of a line like we have in the past. But your author really is bent on introducing you to this point slope form, ladies and gentlemen, in section 2.5 here. So I'm going to go to the textbook right now. I want to, and hopefully things are cooperating. I wanted to go to page 222. Okay, page 222 in the textbook. All right, so let's try this out. All right, and on page 222, I wanted to go over number 12 here. All right, for these problems here, it says write an equation of the line having the given conditions, write the answer in slope-intercept form if possible. Problem number 12. We have seen a problem like this, but in the past, ladies and gentlemen, we used the slope-intercept form to write the equation of the line. I'm going to do the same thing that we did a couple of days ago, only now I'm going to use the point slope form to write the equation of this line that contains these 2 points. All right, so we have 2 points that the line contains or passes through, and we are to write the equation of this line. The first thing we need to do is to find the what of the line.
Slope.
Need the slope. And to find the slope m, we're going to use our slope formula, y2 minus y1 over x2 minus x1. Change in y over change in x, rise over run. I'm going to call this point my x1, y1 point. I'll designate this one as being my second point. Again, it does not matter which point you call which. Dropping the values in to where they belong into the formula. Y sub 2 is -3. Subtract y sub 1 is 8. X sub 2 is -7. Subtract x sub 1 is -4. So the numerator is going to be -15 and the denominator is going to be -7 plus 4 or -3. This reduces down to it reduces down to 5. So ladies and gentlemen,
-15?
what's that?
I thought it was -11.
I'm sorry. I guess I didn't hear you. What was the thing? Wait a minute.
Oh, wouldn't that be
That's
-11?
-11. You're right. My bad. So the slope will be 11/3, correct? when all is said and done. That's what I get for rushing through a math problem. All right, 11/3, ladies and gentlemen, is the slope. All right, now we know the slope is 11/3. We're going to choose one of our points, and it doesn't matter which one we choose. I'm going to go with the first one. So I will go with -4.8 as being my point x1, y1. You could have just as well have chosen your second point to be your point x1, y1. Using the point slope form now, ladies and gentlemen, we can derive the equation of this linear relationship here. So therefore, we got y minus y1 is equal to your slope times quantity x minus x1. Now we put things into the point slope form. Y minus y sub 1 is positive 8. Their slope we found was 11/3 times x minus x sub 1 is going to be the x coordinate of the point I chose, which is -4. And you have the equation of this line. The equation is in point slope form, though it is not in slope intercept form. We can solve this equation for y to get it in the slope intercept form, and your author wants us to do that. So I am going to do that. X minus a -4 is x plus 4. Distributing the 11/3 inside the parentheses. 11/3 times x is 11/3 x. 11/3 times a plus 4.
Why wouldn't the 11/3 be a negative in that equation?
The slope is positive.
Oh, okay, all right.
Positive 11/3 here. We had a -11 over -3. I call it a positive. This is a positive 11/3. So it's a positive 11/3. Distributing 11/3 inside parentheses, 11/3 times x, 11/3 x. What's 11/3 times 4 over 1? That would be 44 over 3. One last step to getting y by itself is adding 8 to both sides of our equation. So we add 8 to the left where it will disappear, and we add 8 to the right. Need a common denominator of 1 and 3, which is 3. An equivalent fraction, therefore, of 8 would be 24 over what, 3? So what's 44/3 plus 24/3?
68 over 3.
So the equation is going to be 11/3 x plus what? 68 over 3. And ladies and gentlemen, you have the equation of that line, or the equation of that linear function that passes through, or whose graph passes through these 2 points here, okay? So in order to derive this equation, this time around, we used a different form called point slope form. You could have just as well have used slope intercept form, plugging in one of these points in for x and y and solving for the y intercept and then deriving your equation that way. That would work. But your author wanted us to use point slope form to derive this equation. Do we understand what just happened there? Any questions? First of all, we had to find the slope of the line, notice, and then we went from there. You would get the same equation if you chose to use -7, -3 and incorporate that into your point slope form. Your slope intercept form would be the same equation in the end also, okay? Any questions, ladies and gentlemen, how I modeled those 2 ordered pairs according to a linear function or linear equation? Do we understand what just happened there? All right. That's called point slope form. Okay. Whoops, hold on again. I don't want to share anything. All right. Parallel lines. What are parallel lines, ladies and gentlemen?
Lines that never cross.
Yes, parallel lines are lines that never intersect each other in the plane. They will never cross or touch each other anywhere in the XY plane. And what do you think the relationship has to be with the slopes of parallel lines?
Same slope.
Yeah, because parallel lines never intersect, ladies and gentlemen, they must have the same slant. If one of these lines has just a slightly different slant than the other one, it eventually will intersect the other one. Do you agree? So parallel lines have equal slopes. That's always true. Parallel lines always have equal slopes. Must be the case. If that's not the case, the lines will intersect somewhere, guaranteed. Perpendicular lines. What are perpendicular lines? What do perpendicular lines look like? Do perpendicular lines intersect?
Yes, they do.
Yes, they do. They intersect at how many points? Perpendicular lines intersect each other in how many points?
1.
1. Ladies and gentlemen, furthermore, perpendicular lines, when they intersect, form what type of angles to each other?
90 degrees.
90-degree angles. This is a right angle. This is a 90-degree angle or right angle. This is a right angle. This is a right angle. It makes sense because 90 plus 90 plus 90 plus 90 is 360 degrees. Do you agree? All right. Ladies and gentlemen, do you want to take a guess as to what the relationship must be with the slopes of perpendicular lines? Parallel lines must have the
to be
same
the
slope.
opposite.
What's that? Go ahead.
Do they have to have different slope?
They have to have different signs. You got that right. There's also one other requirement.
Oh, and the inverse, I guess.
Oh, in a reciprocal, say reciprocal, okay? So, ladies and gentlemen, perpendicular lines have what are called negative reciprocal slopes. Negative reciprocal slopes. Now, what is that saying? Well, suppose the slope of this line here, I'll call line 1. Suppose the slope of this line is like 2/3. Rising line, positive slope, correct? This line is a falling line. So its slope better be not positive, but what?
Negative.
Negative. And ladies and gentlemen, if I call this line 2 here, its slope would have to be the negative reciprocal of 2/3. So therefore, the slope of this line, this falling line, would have to be -3/2. These are called negative reciprocals of each other. Everybody see that there? They're opposite in sign and the reciprocals of each other. They're called negative reciprocals of each other. If lines have negative reciprocal slopes, they are perpendicular to each other in the plane. All righty. Any questions about that? All right, let's go back to page 222 and attempt another problem. Problem number 24 here, ladies and gentlemen. It says for these, A, determine the slope of a line parallel to the given line if possible. B, determine the slope of a line perpendicular to the given line if possible. So I am going to do problem number 24, and this hangs out on page 222. Problem 24. So number 24, they give us the slope of a line as what? +6/7. For part A, ladies and gentlemen, what would be the slope of a parallel line? If a line is to be
6/7.
parallel to this line, its slope would also have to be what? 6/7? Notice the symbolism here. This little symbol means parallel lines. The slope of our parallel lines would also have to be 6/7. What would have to be the slope of our perpendicular line? Notice the symbolism. Slope of perpendicular line would have to be equal to what?
-7/6.
-7/6 would have to be the slope of a line if it is to be perpendicular to this line. Its slope would have to be the negative reciprocal of this slope. Okay? Does that make sense, that problem there? That's all they wanted. Just the slope of a parallel line and the slope of a perpendicular line to this line who has this slope. That's all they wanted. All right, that one's done. That was a pretty simple problem, wasn't it? What if I make one up here? What if I say, ladies and gentlemen, the slope of my line is 0? What would have to be the slope of a parallel line if it's to be parallel to this line?
0.
0. What would have to be the slope of a perpendicular line? What would have to be the slope of a perpendicular line to this line?
Would it be undefined or?
Yeah, because zero, see, the slope of this line is zero. This means this is what kind of a line? It's a horizontal line. Do you agree? Horizontal line, since it has a zero slope. And ladies and gentlemen, what's the negative reciprocal of 0 over 1?
1/0.
Negative 1 over 0, which is called what? Undefined. What kind of a line, ladies and gentlemen, has an undefined slope?
Vertical.
Vertical. Does this make sense, this problem? Why this line would have to be a vertical line? Look at this line's horizontal. And to be perpendicular to a horizontal line, the other line has to be what? It has to be vertical. Doesn't that make sense? So if the slope of our horizontal line is 0, the slope of the vertical line has to be undefined. True? That makes sense there? Okay. The X and Y axis are perpendicular to each other, ladies and gentlemen. What's the slope of the X axis? Anybody? What's the slope of the X axis?
Y = 0.
Well, the slope is just what? I don't want the equation. I just want the slope of the X axis is what? 0? So what's the slope of the Y axis? Not 0. Undefined. The Y axis is a vertical line, correct? The X axis is a horizontal line. So the slope of the X axis is 0, but the slope of the Y axis is undefined. All right, let's go back to our book. All right, problem like number 30 here. What do they want us to do? Well, it says, determine if the lines defined by the given equations are parallel to each other, perpendicular, or neither. I have a question. How could lines be neither parallel or perpendicular? What would they look like, ladies and gentlemen, if lines are two lines are neither parallel or perpendicular? Would
If
they
they
intersect?
cross, but
Okay.
they don't cross at a 90-degree angle.
Yeah. So lines that are neither parallel or perpendicular would have to be lines that, you know, that do intersect somewhere. But you're correct. They do not intersect and form 90-degree angles to each other. This would be considered the case where you have what? Not parallel or not perpendicular. Okay, what they're calling neither. All righty. Okay. So let's go back to our problem here. And so, ladies and gentlemen, problem number 30, they give us equations for some linear functions here. The first one is y equals 4/3 x minus 1. And the second equation, function they give us is y is equal to negative 3/4 x plus 5. All right, both of these linear equations or functions are written in slope-intercept form. So what's the slope of this this function right here? What's its slope? 4/3. What's the slope of this linear function here?
Negative 3/4.
Negative 3/4. Are these slopes equivalent to each other? They're not equal to each other. So are these lines parallel?
No.
Not parallel. The slopes are different. So they're not parallel lines. Might they be perpendicular lines, ladies and gentlemen? Are these slopes negative reciprocals of each other?
Yeah.
These are negative reciprocals of each other. So these lines are perpendicular. And if you were to take the time to graph both of those lines, you would discover that they indeed do intersect at right angles. So these are perpendicular lines here. All right, perpendicular. That makes sense? Those are negative reciprocal slopes, so they're perpendicular. All right, like number 30. Let's go back to our book. One like number 32, ladies and gentlemen, are these parallel lines, perpendicular lines, or neither for 32? Well, harder to tell because these equations are not in what? Slope-intercept form. Can we get these equations into slope-intercept form? Do you think that's possible? You think we can solve these equations for y to hammer them into slope-intercept form?
Yes.
Let's do that. How do I solve this equation for y? Right here. How do I solve for y? First move would be to do what?
2x.
This is a plus 2x. Let's subtract 2x from both sides. Let's move the 2x over to the right side. 2x's drop out on the left, leaving you with 3y. On the right side, we have 7 minus 2x. I'm going to spin the terms around and call it negative 2x plus 7. Divide both sides by 3. And ladies and gentlemen, our equation now is in what? Slope-intercept form. Right? This equation's in slope-intercept form. Let's do the same thing for this one. Put it in the slope-intercept form. To do so, we have to solve for y. I'm going to subtract 2 from both sides. Hence, we have 4x minus 2 is equal to negative 6y. These 2's drop out. Dividing both sides by a negative 6 to solve for y. Hence, we're going to have 4 over negative 6 times x plus a negative 2 divided by negative 6 equals y. Spinning the whole equation around, I want y on the left. Y is equal to, now this negative 4 6, can we reduce 4 over negative 6?
Yes.
Reduces down to negative 2/3, doesn't it? The y-intercept reduces down to plus what, 1/3? Ladies and gentlemen, are these lines parallel, perpendicular, or neither?
Parallel.
Notice the slopes are equal. And since we have equal slopes, these lines are parallel lines. How do I know they're not the same line? Ladies and gentlemen, they're parallel lines, but how do I know they're not the graphs of the same line? Because any line's parallel to itself, is it not?
Yeah.
The y-intercepts are different.
Now notice these y-intercepts are not the same. This line would go to the y-axis at what, 2 1/3. This graph of this linear function would go to the y-axis at 1/3. They're different lines. They're not the same line. They're parallel lines. Okay. By the way, I take that back, ladies and gentlemen. One line in the plane is not parallel to itself because it intersects itself at an infinite number of points, does it not? All I wanted to point out, the only point I wanted to drive home here is the fact that these are not the same lines, correct? So they are indeed parallel to each other because they're not the same line. Y-intercepts are different. All right, that's number 32. All right, number 38. Let's go back to our textbook. For these problems here, it says write an equation of the line satisfying the given conditions. Write the answer in slope-intercept form if possible and in standard form with no fractional coefficients. Problem 38, ladies and gentlemen, that's the one we're going to tackle. Notice for 38, they give us some information about a line. They tell us that the line must pass through what point? 3, -1. And they tell us something else about this line. The line is also parallel. It must be parallel to the linear function -3x plus y equals 4. So, ladies and gentlemen, what would be the equation of our line that contains this point 3, -1? That contains this point 3, -1 and is also to be parallel to this line. What's the first thing we need to find? Anybody? What do we got to find?
The slope.
We need the slope. And since our line is to be parallel to this line, the slope of our line must be what? Must be the same as the slope of this line.
-3x.
So let's solve this equation for y to put it in the slope-intercept form. Presently, this is in standard form. We want to solve it for y to hammer it in the slope-intercept form. To do that, we add 3x to both sides. Notice how I added 3x to the right. 3x's drop out on the left, leaving you with y is equal to 3x plus 4. What is the slope of this line? 3. So, ladies and gentlemen, so our line must have what slope? Our line must also have a slope of what?
3.
3. True, because it is to be parallel to this line, correct? So now we know the slope of our line must be 3, and it must contain the point what? What point does it contain? 3, -1. So how can we write the equation of this line? You could do it one of 2 ways. You could write the equation of this line using slope-intercept form or point-slope form. I don't really care which method you choose in all honesty, but since this is kind of slanted towards the point-slope form, let's do that. Our choice is use the point-slope form. Y minus y1 equal to your slope m times x minus x1. That's your point-slope form. So therefore, this point here is going to be our point x1, y1. We feed things in and substitute them in where they belong into the formula. So y minus y1, y1 is what? -1 is equal to my slope, which we determine as 3, times x minus x1, x1 being 3. Ladies and gentlemen, this is the equation of our line that would be parallel to this line, okay? Your author wants your answers in 2 forms, slope-intercept form and standard form. First, we'll get it into what? Slope-intercept form. How do I begin to do that? How do I hammer this into slope-intercept form? How do I get this into slope-intercept form?
Distribute the
Okay,
3.
you can distribute to 3 on the right. That's okay to do that. You can also clean this up. Subtracting a -1 is adding 1. Why not fix that? So therefore, distributing, we have 3x minus what? Minus 9. Now we subtract 1 from both sides to solve for y to get this in the slope-intercept form. So slope-intercept form would be y is equal to 3x minus 10. This is your answer in slope-intercept form. But your author doesn't want you to stop there. Your author also wants your answer in standard form. What's standard form for a linear function? Anybody remember? Standard form.
AX plus BX, BY equals C.
Yeah, now we got to hammer our equation into this form. Furthermore, they stress that our coefficients better not be fractions. They better be, integers, okay? So ladies and gentlemen, let's feed off of our slope-intercept form and hammer it into standard form. How do I do that? How do I get this equation in slope-intercept form into standard form? Anybody?
Subtract the 3x from both sides.
Yeah, we got to get the x and the y on the same side of the equation. Do you agree? That's a requirement to be in standard form. So let's minus 3x from both sides. I'm going to flip these terms around, by the way. Instead of saying y minus 3x, I'm going to bring it out as -3x plus y, saying the same thing. These x's drop on the right, and we're left with -10. Ladies and gentlemen, this would be standard form now. And notice our coefficients are not fractions as required in the instructions. They are integers. That's your answer. Any questions how we tackled this problem here? First of all, they wanted us to find the equation of a line that contains this point and must be parallel to this line. The first thing we had to do is find the slope of this line. We did so by hammering it in the slope-intercept form. We then determined the slope of this line is 3, so the slope of our line has to be 3 since it must be parallel to this line. Now we know the slope of our line, we know a point that sits on our line, we should be able to write the equation of our line. And we did so by using point-slope form. Correct? Any questions about that problem there, ladies and gentlemen? How we tackled it? That was one like number 38. One like number 40 now, ladies and gentlemen. They want us to write the equation of a line that passes through the point 5,4 and is to be perpendicular to the line x minus 2y equals 7. So our line is to contain what point? 5,4. And it must be perpendicular to what line? To x minus 2y equals 7. So ladies and gentlemen, to write the equation of our line, what's the first thing we need to determine?
The slope.
We got to get the slope of this line. So the first thing is we need the slope. Need the slope of x minus 2y equals 7. To determine that, we can hammer this equation in the slope-intercept form. To do that, we have to solve for y. To do that, we have to what? Subtract x from both sides to kick this thing off. The x's drop on the left, leaving you with negative 2y. And on the right, I'm going to flip these terms around and call it negative x plus 7. Now we divide both sides by negative 2. These negative 2's reduce to 1 on the left, leaving you with y. And on the right side, ladies and gentlemen, I have negative 1 over a negative 2. What's a negative 1 over a negative 2? Equivalent to really a what?
Positive.
Positive. So we will call this positive 1/2 x. 7 divided by negative 2 is a minus 7/2. There's this equation. This equation now is in slope-intercept form. Therefore, what is its slope? 1/2. So our slope must be what, ladies and gentlemen? Since our line is to be perpendicular to this line, what must its slope? That's right, it's got to be the negative reciprocal of this. So our slope must be negative 2 over 1, or you could just say negative 2. Negative 2 is the negative reciprocal of 1/2. These are negative reciprocals. So now we know the slope of our line must be negative 2, and we know our line contains the point what? 5, 4. So now we should be able to write the equation of our line. And I, again, will use point slope form. So here it is, using point slope form, y minus y1 is equal to your slope m times x minus x1. We substitute things in where they belong. So we have y minus y1, but what's y1? Y1 is 4. So y minus 4 is equal to your slope m, which we determined as negative 2, times quantity x minus x of 1, x of 1 being 5. This is, ladies and gentlemen, the equation of our line. And this line here would be what? Perpendicular to this line here. These two lines are perpendicular to each other. Your author wants you to get this into two forms, slope-intercept and then point in and also standard form. To get this in the slope-intercept form, what do? First, we can distribute the negative 2 inside the parentheses. So we got y minus 4 is equal to negative 2x plus 10. Adding 4 to both sides. Our equation in slope-intercept form is y equal to negative 2x plus 14. That's your equation in slope-intercept form. Finally, they want our answer in standard form. So standard form. In standard form is ax plus by equals c form. Meaning, if I use my slope-intercept form, I have to get x on the same side of the equation with y. To do that, we add 2x to both sides. Hence, we have 2x plus y is equal to what? These two x's drop out and we're left with 14. This, ladies and gentlemen, would be the equation in standard form. We have our answers. So this is our equation in slope-intercept form. This is the same equation in standard form. Both these equations would be what? Perpendicular to this one right here. Questions how we did that problem? There's your answer. Okay. That's one like number 40. One like number 52. Oh, let's see here. All right, now, ladies and gentlemen, we're going to start applying linear functions to everyday problems, okay? Application problems. And, you know, I really think that's where the beauty of math lies, is being able to apply it to the real world. I think I've indicated that in this class before. Math is great, but in my estimation, it only becomes greater if you can apply it to things in our everyday lives. So let's see if we can apply linear functions to actual, problems that would be relevant out there in the real world. Number 52. Number 52. This is on page, what page is it? 223. On page 223, 52. At a parking garage in a large city, the charge for parking consists of a flat fee of $2 plus $1.50 per hour. So ladies and gentlemen, if you just go into that parking structure and just go around and pull out, you're still gonna have to pay what? You gotta pay the $2. Do you agree? If you just go into that garage, even for 1 second, you're still gonna pay $2. That's a guarantee. But you're gonna pay $1.50 each additional hour your vehicle's in that parking structure. Write a linear function to model the cost for parking. P of T is the price to park in that garage for T hours. They want you to come up with a linear function that models this situation. All right. So, ladies and gentlemen, how are we going to do that? Well, what was T again? What did T represent?
Time.
Time in hours we parked in the garage, correct? That's what they're going to charge you. Excuse me, that's the number of hours that we will have parked in the garage. So ladies and gentlemen, what is going to be the total cost when you park in this garage for T hours? Well, you know you're going to be laying out that what? Flat rate of $2 just to go into the garage. You have to lay out $2 guaranteed. Plus, you're going to be paying not only a fixed cost, ladies and gentlemen, oftentimes we call this a fixed cost. Fixed cost. But you're going to be paying a variable cost. And what is the variable cost? What variable cost are we going to realize here? We park in the garage for T hours. They charge us how much per hour? I believe it's $1.50. So the variable cost is going to be $1.50 per hour times T hours that we're in the garage. Ladies and gentlemen, we're starting to form a relationship for the total cost of having parked in this parking structure. But they're not calling total cost these words total cost. They're calling the total cost P of T. Ladies and gentlemen, flipping these terms around, I have modeled the cost of parking in this garage according to a linear function. You are looking at that linear function. This is your answer for part A of that question. We have modeled the cost, the total cost of being in that garage for T hours according to a linear function. P of T is the what again? What is P of T? It is the
Total cost.
total cost of having been in that garage. What's T again?
Time and hours.
The time and hours we were in garage. Ladies and gentlemen, what's the slope? What's the slope of this line? This linear relationship?
3/2.
Okay, 3/2, but well, we'll leave it in dollars, in a dollar figure since we're talking about money. So the slope here, you're right, is as a fraction, it'd be 3/2, although I'm just going to leave it like this. Can anybody interpret what the slope is saying? What is this slope really saying? How do we interpret what the slope is saying in the context of this problem? What's that really saying? What was that $1.50
It goes up $1.50 for every hour.
for every hour? Ladies and gentlemen, slope is a rate. It's a rate of change of Y with respect to X. In this case, it's a rate of change of cost versus time. The slope is to be interpreted as they're going to charge us $1.50 per every what? Per every hour our vehicle's in there. Per means rate. If you drive 50 miles per hour, that's the rate that you're driving your car. $1.50 per hour, that's the rate we are being charged for keeping our car in this garage. That's a rate. Slope is always a rate of change. In this case, it's a rate of change of cost versus time. $1.50 per hour. Does anybody want to interpret for us what the y-intercept is? The y-intercept is 2. What does 2 really mean in the context of this problem? What was 2?
Flat cost.
It's the fixed cost. I mean, it's the fixed cost for even just venturing into the garage, whether we're going to stay in there for 1,000 hours or we're just going to drive in and drive right back out. We're still going to have to lay out $2 because we went into the garage. All right, that's your fixed cost. And ladies and gentlemen, I have explained what all these terms in this linear function represent. Okay. Part B, what is part B of that question? It says for 52B, evaluate P of 1.6 and interpret the meaning in the context of this problem. Ladies and gentlemen, we're going to evaluate this linear function at 1.6. Mechanically, what does that mean to do? Mechanically, it means to take 1.6 and substitute it in where? Where do I put the 1.6?
P.
In for T. 1.6 goes in for T into the definition of this function that we developed, this linear function. So P of 1.6 is going to be 1.50 times 1.6 plus 2. Get on your calculator and help me out here, ladies and gentlemen. What is 1.5 times 1.6 plus 2? Anybody dial it up for me? What does this evaluate to?
4.4.
4.4. Does anybody want to interpret what's going on here? What have we just generated in the context of this problem? What does 1.6 represent? What is 1.6?
Time.
Time. Ladies and gentlemen, we were in the garage for what period of time? 1.6 hours. That's the time we parked in the garage. What's the 4.40? What does this represent?
The cost of the amount of time we spent.
This is the total cost. Yeah. This is the total cost of having parked in that garage for 1.6 hours. That's it. That's how we interpret what this is saying in the context of our problem here. So if you park in that garage for 1.6 hours, you're going to be paying $4.40. By the way, how many minutes is 6/10 of an hour, ladies and gentlemen? 6/10 of an hour is how many minutes? 60 minutes in an hour. What's 6/10 times 60? What's 0.6 times 60?
120.
0.6 times 60.
36.
So that means we will have parked in the garage for precisely 1 hour and what?
36.
36 minutes. You park in that garage for 1.6 hours, better known as 1 hour and 36 minutes, you're going to be laying out $4.40 in cost. Okay. All right. Does that make sense, that problem there? How we modeled that situation according to a linear function for part A, and then we use that linear function to answer a question. Okay. All right. So we're done with that one. That was one like number 52. Let's move on. How about one like number 56? Okay, in this problem here, ladies and gentlemen, they want us to answer everything, okay? So in problem 56A, they want you to write a linear cost function that represents the cost C of X to produce X items. B, write a linear revenue function that represents the revenue R of X for selling X items. C, write a linear profit function that represents the profit P of X for producing and selling X items. D, determine the break-even point. This is a question that you would probably see like in a course in economics or finance. All right, so ladies and gentlemen, the information they give us in problem 56 is they say that our operation in manufacturing these widgets, whatever it is is a fixed cost of $2,275. The variable cost to produce any item, to produce one of these widgets, whatever the widget is, you can replace it with whatever you want, a television, computer, whatever. The variable cost for producing any one of these items is $34.50. That's called the variable cost. The price at which the item is sold is $1.30 a piece. The price item is sold for, they tell us, is $1.30. Armed with all this knowledge, in part A, they want us to generate a cost function. So given all this information in this problem, ladies and gentlemen, they want us to find a cost function. They want us to find C of X, which C means cost.
The first two, the fixed costs and the variable costs are from 55, not 56.
Oh, geez. All right, so we're doing a different problem here. You're right. Should be 5625 and 0.40. 5625 and 0.40. This should be 5625 and 0.40. Thanks for telling me that at the beginning of the problem as opposed to waiting till the end. Thank you. I've had students just wait to the very end after I filled the whole board up, ladies. I'm just watch me sweat. And then they'll say, Mr. O, you were doing some other problem. All right, ladies and gentlemen, we want to develop a cost function here. Now, do we know how many of these widgets we're producing? We don't know what it is. Let's declare it as a variable. Let X be equal to the number of widgets. Now, when I say widget, ladies and gentlemen, that's a hypothetical term for meaning we could be producing anything, okay? Number of widgets produced. And what? And sold. And sold, okay? So, ladies and gentlemen, if we produce X widgets, how much cost are we going to incur? Well, for one thing, we have our fixed cost. We have to lay out that $5,625. Maybe this fixed cost might be the cost just for the raw materials to make our widget. And the variable cost might be the cost that we pay our employee per, I don't know, hour or a minute or something, whatever, to make these widgets. So the cost we're going to incur is the fixed cost plus the variable cost. The variable cost is 40 cents per what? Per widget. We're manufacturing X widgets. And so, ladies and gentlemen, the variable cost is going to be 40 cents per widget times X widgets. Or technically, this is 40 hundredths of a dollar. 40 hundredths of a dollar per widget times X widgets. This is the linear function that models the cost of our production process here. So therefore, the linear function C of X, I'm going to spin these terms around so it's in slope-intercept form, is 0.40x plus 5625. That's your answer for part A. That's your cost function. It's a linear function. The more widgets we produce, the more cost we're going to fathom, bottom line. Part B, they wanted us to develop what next? I believe was it a revenue function? Revenue function, ladies and gentlemen, what's revenue? We know what cost is. That's money we're going to have to lay out. What's revenue?
The money you make.
That's money we bring in. They want us to find a revenue function. And this is one that's of great interest to us because we want to know how much we're going to make. So, ladies and gentlemen, revenue for selling X of these widgets. The revenue is going to be what? What do we charge per widget? What's our price per widget that we charge our customers?
$1.30.
$1.30. And we're going to sell X of them. We will assume we sell X of them. So our revenue that we bring in, if we sell X of these widgets, is going to be $1.30 per widget times X widgets. That's your revenue function. That's your linear revenue function. That one's done. C. Now they want us to find, ladies and gentlemen, a profit function, P of X. Does anybody know what profit is?
Money you make. after like what you pay?
Yeah, exactly. You see, revenue is money we're gonna bring in. But ladies and gentlemen, we gotta pay our bills. We gotta pay our costs. After we pay our costs, then anything remaining is called the profit. And we hope our profit is positive rather than negative. If it's negative, we're either gonna have to charge more for our item, or else we're gonna have to file bankruptcy. Do you agree? We're going under. All right, ladies and gentlemen, profit. What is profit? It's your revenue function minus your cost function. Profit is revenue minus cost. So we're going to take these two functions, our revenue and our cost functions we developed in the previous problems. We're going to subtract them to develop a profit function. So my profit function for manufacturing and selling X widgets is going to be the revenue, which is 1.30x, subtract the cost. The cost being this 0.40x plus the 5625. Now, simplifying this, distributing the negative sign throughout the parentheses and gathering together like terms, we therefore have 1.30x minus 0.40x minus this 5625. Combining the like terms of x, our profit function simplifies to what's 1.30x minus 0.40x?
0.9x.
Yeah, 0.90x minus the 56 what? 25, correct? Ladies and gentlemen, this is our revenue function. This indicates, excuse me, not our revenue function. This is our profit function. It indicates the amount of money we're going to make and get to keep that goes into our account, our bank account, after we sell, manufacture and sell X widgets. All right, now for part D, they want us to find what? They want us to determine the break-even point. Ladies and gentlemen, do I have any business people in this class? What's the break-even point in the business world?
When you start making profit.
When you start to make profit, break-even point. Okay, so ladies and gentlemen, break-even point occurs when your revenue is equal to your cost. When your revenue, the money you're bringing in, is equal to the money you're laying out in cost, you have broken even. That's called the break-even point. You're not making money, but you're not losing money either. It's called the break-even point. They want us to find that break-even point. So ladies and gentlemen, how are we going to do that? What we're going to do is we're going to take our revenue function we developed above, which is 1.30x, and we're going to set that equal to our cost function we developed above, which is 0.40x plus 5625. To solve this equation, ladies and gentlemen, we could solve it, algebraically, but let's have a little fun. Let's try to solve this graphically. Does anybody remember how we solve equations graphically on the calculator? Anybody remember how we do that? Did I not set what? The left side equal to what? Y sub 1 on my calculator? And set the right side equal to what? Y sub 2? Then we graphed both of these functions and then look for a point of intersection. Do you agree? Between the revenue and the cost function? That'll be the break-even point, that point of intersection. Let's turn this over to the calculator. So I go grab my calculator. Bear with me for a sec. I hope she's working today. Sometimes I feel like I got a Commodore 64 computer here back in 1982. All right, ladies and gentlemen, let's try to do this now. Using the calculator, go to your equation editor, y equals. For y1, I want you to type in your revenue function, 1.30x. That's your revenue function. For y2, I want you to type in your cost function, 0.40x plus your fixed cost of $5,625. Now we're going to graph both these functions and we're going to look for that point of intersection, because that point of intersection means the left side of this equation is equal to the right side of the equation for some particular x value. That is called the break-even point that we're searching for. I'm gonna look at my window. Notice my horizontal and vertical axis are all screwed up. I'm gonna go to zoom to put them back into the default mode of -10 to 10 by 1 on both axes. So I'm gonna go back to Z standard, ladies and gentlemen. Zoom Z standard. We'll put your axes back from a -10 to a maximum value of 10 by 1. And notice we can see one of our functions, but we can't see the, we cannot see the other one, can we? Anybody know why we cannot see the other one? Think about it, ladies and gentlemen. Look at this. Why can we not see the graph of our cost? Why can we not see the graph of our cost function? Look at
It's
this.
gonna be the same to break even.
Yeah, look at this y-intercept, 5,625. I've only told my calculator to go up as high as +10 on the y-axis. No wonder we can't see the cost function. Look at how large that y-intercept is. We can easily graph this thing and see it, but we're not going to see this one. We got to go up higher on our y-axis big time. All right, so we got to go up higher on that y-axis. We're never going to see that cost function until we go up to at least about 6,000. So go to window, ladies and gentlemen. I want your Y max value to go up to about 6,000. It has to go up there. We're not going to see the graph. All right, now I'm going to have my y-axis increment then by 100 units instead of 1 unit apart. Let's hit graph and see if we've accomplished anything. Well, we can start to see the graph of the cost function, but we're having a heck of a time trying to see the graph of the other one now. Do you agree? Now the other one's messed up. So we're having a real heck of a time here, ladies and gentlemen. We may have to go further out on the x-axis. I don't know. We might have to go up higher on the y-axis and further out on the x-axis. I'm going to go to 10,000 on the y-axis for a maximum value. On the x-axis, I'm going to go out to maybe 1,000. Have my tick marks on the x-axis spaced 100 units apart instead of 1. Let's try this scaling, see if we can see it now. Well, there's the revenue function. Here comes the cost function. Do you agree, ladies and gentlemen, eventually these lines are going to intersect? They will intersect eventually, but they're going to intersect far to the right on our x-axis. We have to go farther to the right on the x-axis. 1,000 is not far enough. Heck, we might have to go out to 10,000. Let's try this scaling. Aha! Do you agree? We can now see the graphs of the cost and the revenue functions, the left and right side of that equation. Here's the window setting I chose, ladies and gentlemen, right there. That's a good window setting. You might have to tinker with your window setting to solve these equations graphically. It happens all the time. All right, now we got to find a point of intersection. Does anybody remember how to find the point of intersection? How do we do that?
Hit second and then hit trace.
Yeah, we got to go into our calculate mode. Second, trace, and go down and grab what function? Intersect function. Ladies and gentlemen, second trace gets you into calculate. Go down and get the intersect function. Hit enter. That'll be called our first curve. Hit enter. That's our second curve. Hit enter. Hit enter again. There's your point of intersection. Ladies and gentlemen, how do we interpret what that point of intersection is saying? Does anybody want to interpret what that point of intersection is saying? That's 6,250, 8,125. What is that point? What is that point really saying? How do we interpret what that's saying, that break-even point? This is called the break-even point, when the revenue equals the cost. What is this saying?
You have to sell 6,250 in order to break even at the cost, which would be
And the revenue, which would be,
and the revenue.
that's correct. Ladies and gentlemen, we must sell, well, we must manufacture and sell 6,250, again, widgets, because I don't know what we're manufacturing here, okay? To have the cost, the revenue and the cost equal to what? They better be equal to $8,125. Do you agree? And our profit, ladies and gentlemen, will be what? What will be our profit if X equals 6,250 widgets manufactured and sold? Our profit would have to be equal to what? What do you think? What's our profit got to be equal to? Break-even point. Are we making any profit? Break-even point would be $0. We're not making money, but we're not losing money. Let's check our answer. What was our profit function? Anybody remember a profit function we developed? It was 0.90 x minus 5,625. Let's check our answer by evaluating our profit function at 6,250 widgets. What's 0.90 times 6,250 widgets minus 5625? What does this give us? What it had it better give us? Our profit better be equal to what? 0 at the break-even point. We're not making any profit. We're not losing money either, but we're not making any money either. It's called a break-even point, ladies and gentlemen. Is it 0? Does this evaluate to 0?
Yes.
Okay. You see how this is all working here? So math is used in the business world quite a bit, used a lot in economics. A lot of math, a lot of functions are used in economics, ladies and gentlemen. Okay, let's go back and dig up our book again. That was one like number 56. One like number 58. The cost and revenue functions C and R are shown for producing and selling X items. Determine the values of X for which, ladies and gentlemen, they give you the graph of a revenue function in red and a cost function in blue. Both are linear functions. Notice. For part A, in order for our revenue to be equal to the cost, that's called your break-even point. Ladies and gentlemen, how many widgets must we produce and sell to break even? X must be equal to what? What's X equal to at the break-even point?
25,000.
We must manufacture and sell 25,000 widgets, ladies and gentlemen, to break even, where the revenue will be equal to the cost. How many widgets must we sell, ladies and gentlemen, in order for the revenue function to be less than the cost function? And if revenue is less than cost, that means we're bringing in less money than we're laying out. That means we're in trouble. We're losing money. Ladies and gentlemen, the break-even point is 25,000 widgets. Do you agree? Notice for X values less than 25,000, the red line is below the blue line. That's a bad thing because that means your revenue is less than your cost when the red line is below your blue line. So do you agree if we manufacture less than 25,000 widgets, we're going to lose money? Our revenue is going to be less than our cost. Isn't that true? All right. For how many widgets must we produce and sell in order for our revenue to exceed the cost, to be larger than the cost? That occurs when the red revenue line is above the blue cost line. That occurs if we sell more than 25,000 widgets. We will make more money than we're laying out. Does that make sense, sir? That problem? All right, that one's done. All right, one like number 64. All right, in this problem here, it says the graph shows the number of students enrolled in public colleges for selected years. And this is authentic data, according to the National Center for Education Statistics. The X variable represents the number of years since 1990, and the Y variable represents the number of students in millions. They want you to use the points 4, 11.2, and 14, 13.0 to write a linear model for this data. They want us to write a linear function or equation that models this data, ladies and gentlemen. How are we going to do that? And can somebody interpret for me what these points are even saying? 4, 11.2 and the point 14, 13.0. What are these points even saying? What was X again? X represented what?
Number of years,
The number of years since what year? What was the starting year?
1990.
1990. Y represents what? What's Y?
The number of students,
The number of students and in what? In millions, right? In millions. So, ladies and gentlemen, now that we know what X and Y represents, can somebody interpret for me what this point is saying here? What's this ordered pair saying? How do we interpret what it's saying?
4 years and 11.2 million students.
In the year what? If X is equal to 4, ladies and gentlemen, what year is that? 4 years after 1990. This is 1994. In the year of 1994, how many students attended public colleges? 11.2 students? Only 11.2 students? No. 11.2 what?
Million.
11.2 million students attended public colleges. Okay. How do we interpret what this point is saying? What does 14 represent? If X is 14. That's 14
That's
years after.
2004.
Yeah, this will be 2000 and what? 4? 14 years after 1990. This is the year 2004. In the year 2004, how many students attended public colleges? 13 million students attended public colleges. That's how we interpret what these ordered pairs are really saying in the context of our problem. Ladies and gentlemen, we're going to write the equation. So we're going to try to write the equation of the line that contains the 2 points, 411.2 and the point 1413. I will call this my first point, and I will designate this as being my second point. We're now going to turn it over. Well, first we have to find the what of the line. Must find what first? What do we got to find first, ladies? I'm gonna write this equation.
The slope,
Got to find the slope. Got to find the slope first. So we're going to use our slope formula. So therefore, to write the equation of this line, we need the slope. So the slope of this line is going to be y2 minus y1 over x2 minus x1. Based on how I labeled my points, my y2 is going to be 13. Minus y1 will be 11.2. Divided by x2 is 14. Minus x1 is 4. What's 13 minus 11.2?
1.8.
1.8 divided by what? 10? Does anybody want to interpret what this slope is really saying? What is this slope really saying? Can anybody interpret this for me? Yeah, I see. It's 1.8 over 10. What does it really mean in the context of this problem here?
Over 10 years, 1.8 million people. There was a
There
gain
was-
of 1.8.
That's
million
right.
people going to public
Exactly.
college.
Exactly. That's right. So, ladies and gentlemen, it looks like attendance. This is so important. I'm going to take the time to write this out. Attendance increased. Okay. Increased by 1.8 million students in how many years? In 10 years. This is the rate of increase, ladies and gentlemen, in which students are attending public colleges. The rate of increase is 1.8 million students per every 10 years. That's a good thing for the education industry. Do you agree? If that was negative, if this slope was negative, that means the students enrolling in public colleges is decreasing per time. All right, now we know the slope. We need to choose a point. Which point you want to go with? It doesn't matter which point you choose. We got to write the equation on this line here. I'm going to choose the first one. So I'm going to choose this 4, 11.2 to be my point x1, y1. Now we're going to use what? You could use slope intercept form, but your author is really bent on trying to use this point slope form. So to write the equation that models this situation, we're going to use the point slope form. So y minus y1 is y minus 11.2 is equal to your slope. Ladies, this slope is awkward as heck. What's 1.8 divided by 10? Let's just turn this into a decimal, 0.18.
Yeah.
So this really means that for the rate of increase of our student enrollment in public colleges is increasing by 0.18 of a million number of students per every year. 0.18 million students are enrolling in our colleges per year. There's an increase in student enrollees of 0.18 million per 1 year. Okay, that's what that's saying. X minus what, 4? All right, this is our equation that models the situation. We could put it in the slope intercept form if you want to. Distributing the 0.18 into the parentheses, we got 0.18x minus what's 0.18 times 4?
0.72.
0.72, I believe, right? Adding 11.2 to both sides. We get negative 0.72 plus 11.2. What does that give you? What's 11.2 minus 0.72? Anybody?
$10.58.
Okay. Plus 10.58. And there you go, ladies and gentlemen. This models the number of students that are enrolling. So we really have come up with an enrollment function, maybe E for the word enrollment. You agree? This enrollment function now is a linear function.
Oh, sorry, it was 4.8, not 5.8.
4.8. Okay, 4.8. How do we interpret the slope, ladies and gentlemen? The slope is saying that enrollment is increasing by 0.18 million students per what? Per year? What's this 10.48? That's our y-intercept. Anybody want to interpret what this is saying? Your y-intercept. At x equals 0, which is what year? X equals 0, 1990. So ladies and gentlemen, during the year of 1990, there were 10.48 million students enrolled in public colleges. That's how you interpret what the y-intercept is saying. In 1990, when x is equal to 0, right? That's your y-intercept. There were 10.48 million students enrolled. It's very important to be able to interpret what the function's saying. Otherwise, it's a waste of time to even build it. If we can't even interpret what it's saying. The interpretation is critical. All right. So that's quite a problem, isn't it? Quite a problem. All right. Was there any more to that problem? Well, we've answered part A. That's our enrollment function there. Part B, interpret the meaning of the slope in the context of this problem. Ladies and gentlemen, we've already interpreted it. The enrollment is increasing. Why increasing? Because the slope is positive. It's increasing at a rate of 0.18 million students per year. What is 0.18 million? If you multiply 0.18 times 1 million, what is that really going to be? What's 0.18 times 1,000,000? What's 0.18 times a million? Do that on your calculator. What is that?
180,000.
So, ladies and gentlemen, enrollment is increasing by 180,000 students per year. That's the rate of increase in enrollment per year. That's part B. The explanation of this slope is part B. All right, we've answered part B. Part C is interpret the meaning of the y-intercept. Ladies and gentlemen, how did I interpret what the y-intercept is saying? It's saying when x equals 0, which was 1990, there were 10.48 million students enrolled in public colleges. This is the answer to part C of that problem. That's the interpretation of the y-intercept. Part D, in the event that the linear trend continues beyond the last observed data point, use the model in part A to predict the number of students enrolled in public colleges for the year of 2020. So, ladies and gentlemen, for part D, if I use my enrollment linear function, can I predict how many students will be enrolled in public colleges in the year 2020? What would X have to be for the year 2020?
30.
Yeah, 2020 minus 1990 would have to be 30. So we're going to put 30 into our enrollment function for X. So it's going to be 0.18 times 30 plus 10.48. Can you dial this up in your calculator for me? What's 0.18 times 30 plus 10.48? What's our enrollment going to be in the year 2020? If this trend continues, that's the key assumption, that this trend, this rate continues. Okay. What would be our enrollment if this rate continued? What does this give you? Anybody?
1588.
1588?
15.88, my bad.
15.88. So there will be 15.88 what? Million students enrolled in public colleges. That's your answer. That's how many we would predict will be enrolled in the year of 2020, assuming the rate for the previous 30 years is still in effect, or the previous time period is still in effect for this time period, okay? That's the point of developing mathematical models, ladies and gentlemen, is to be able to use them to make predictions, okay? Now, in this problem here, ladies and gentlemen, to build the equation of this mathematical model, we only use 2 points, correct? And because of that, mathematical models are not unique. Excuse me, they are unique in the sense that, ladies and gentlemen, if I chose 2 other points, suppose I had 2 other data points where one of the data points was different than one of these, do you agree I would get a different linear function if I use 2 different points? All right, that can be a problem, because what if we erroneously collected this data point in the field, but it was really not collected correctly, and it was really supposed to be some other data point? That means our mathematical model is all in error here. All right, to circumvent that potential problem, ladies and gentlemen, oftentimes we like to collect several ordered pairs and then try to model several ordered pairs according to a linear equation. The process of doing that, ladies and gentlemen, of modeling several ordered pairs according to a linear function is called linear regression. And linear regression is studied in detail in a statistics course. So in Math 150 here at Mott, you will study linear regression. Linear regression is, like I said, it's building a linear model or function for more than 2 ordered pairs. It's called linear regression. I'm going to show you how to do linear regression, ladies and gentlemen, on a data set, an ordered pair data set now. So have your calculator ready. And by the way, I want you to study in detail. If you miss any of this that I'm about to go over, example 8 in section 2.5 goes over linear regression. Okay, it goes over in detail how to conduct linear regression on a data set that contains many ordered pairs. Example 8, section 2.5. So if you don't get any of this, if you miss some of this, it's regurgitated for you in example 8, step by step. Okay, let's go to our textbook and try to perform linear regression on a data set. We're going to try to do, ladies and gentlemen, number 72 here. Now in this problem here, it says use the data in the table to find the least squares regression line. What does this table even pertain to? Well, it says the data in the table gives the weight of a puppy, ladies and gentlemen, Y in pounds versus X days after adoption. So this child went to a shelter and adopted a puppy, and the weight of the puppy after the adoption date is given according to this table here. So 0 days after adoption, that means the day the child actually obtained the puppy. The puppy initially weighed 11 pounds. 5 days after the puppy was adopted by the child, the weight increased to 12.8 pounds, etc., etc., etc. Okay. How many ordered pairs do you see in this table, ladies and gentlemen? How many ordered pairs? How many ordered pairs do we count?
10.
There's 10. All right, there's 10 ordered pairs. And do you agree that if we took the time, we could plot these 10 ordered pairs in the XY plane? Where the x-axis is the number of days after adoption, the y-axis is the weight of the puppy in pounds. They did that, ladies and gentlemen, back in problem 62. They graphed all those points. And ladies and gentlemen, this is all the points plotted back in problem 62. By the way, there is Dodger. That's the puppy that was adopted. Dodger. Ladies and gentlemen, does it appear that these data points that were collected appear to lie on a line? Does it appear that these points appear to lie roughly on a line?
Yes.
But they're not perfectly all on a line, are they? This point here is a little bit below the line. This point here is a little above the line. But I'll tell you what, for the most part, it appears that these points are collinear points. They appear to lie on a line. Ladies and gentlemen, we're going to write the equation of this line. And this line we're going to come up with fits these data points the best. It's called the least squares regression line. Instead of just using 2 data points to write the equation of a line like we did in the previous exercise, we're going to use all the data points to derive a linear equation or linear function. That process is called linear regression. We're now going to show you how to do that on your calculator. So let's go back to our problem right here. Bring up your calculator. So here's the machine. Wait a minute here. Okay, turn it on. Clear any garbage out. So I want you to go to hit your stat button, ladies and gentlemen. Wait a minute. I want you to go to y equals first and clear out any garbage in your equation editor. You got to get rid of this here. Make sure you don't have any equations to the right of any equal sign in y equals. Clear this field out. Now I want you to hit your stat button. Stat, edit. Notice my cursor is sitting on edit. So we hit enter to dive into the editing mode of our stat feature. In list 1, I want you to type in the number of days since adoption. So I want you to type in, you know, the data points here. So, come on. Well, look at what a hassle. 0. I want you to type in all these data values in list 1, the X data values, 5, 12, 18, 24, 31, 40, 45, 5260. Are you all following me or are you lost? We're entering the first column of this table in the list one in our calculator, stat edit. Are we good, ladies and gentlemen? Anybody lost? Anybody lost? I guess I'll assume that we're not. Hit your right arrow key when you get done, and in list two, I want you to type in the weight of this puppy, 11 pounds, 12.8 pounds, 14.3 pounds, etc., etc. Type all these data values in. Make sure you type the data in correctly. Don't type too fast. You might have bogus entries, and that's going to compromise our results big time.
Counts wrong. Someone, second row.
All right, I think it's Tony coming, speaking. I don't know what it is. The quality of the audio is just terrible. It sounds like you're coming, like you're inside a pipe or something. And it's really muffled. If you want to text me, Tony, you could do that if you have a question. That would be a lot. Chat me your question or whatever. That'd be so much more efficient. Okay, I appreciate that because I just can't make out your audio. So if you have any questions, just chat me. Are we okay? Hold on, I got a chat here. Let's see what it says. You put 1 and not 11. Thank you. Yeah, look at later on when you get done, make sure, come on, what's the deal here? Make sure you go back and, check your data entry quickly. Just scroll through it and you are right. Notice I should have typed in 11 pounds for the first day of adoption. I typed in 1 pound. That would be a very severe error in our investigation here. Make sure you check your data entry quickly. Make sure you have correct data. All right, so everything looks okay. I'm gonna just look at my X data quickly. All right, looks about right. Okay, so ladies and gentlemen, when we get done doing this, the next thing I want you to do now is go into your stat plot mode. Wait a minute. Hold on a second, let me think. Yeah, we can go into stat plot mode. So we hit our second button followed by the Y equals button, second Y equals. And I want you to go into stat plot number 1. Make sure all your stat plots are turned off. If they're not, move your cursor down here to number 4 and hit enter to turn all your plots off. Okay. Second Y equals. I want to go into stat plot number 1 now by hitting enter. Turn stat plot 1 on. So with your cursor sitting on the word on, hit enter to toggle it on. It's now been turned on. Hitting your right arrow key and your down arrow key, I want you to navigate to the scatter plot icon. Ladies and gentlemen, the first icon here is called the scatter plot icon. I'm going to show you how to do a scatter plot so your calculator can plot all these ordered pairs. Select the scatter plot icon, hit enter to select it. Does your X list say list 1? And does your Y list say list 2? It should, because in list 1, we typed the what? X data. In list 2, we typed in the Y coordinate data. Better say L1 and L2. If this is the case, get out of this mode now by hitting second mode to quit. You can hit your clear button. Ladies and gentlemen, now we're going to go back to stat, and we have to perform linear regression. So stat, go over to calculate, hit your right arrow key to go to the calculate menu. Stat, calculate, now go down, scroll down to the linreg function, that's linear regression. So stat, calculate, go down to linreg, that's short for linear regression. Hit enter to activate the linear regression function. Enter. Your X list better say list 1. Does anybody's X list say something different than L1? Anybody? We all say L1 here, correct? All right, your Y list better say list 2. Does anybody's differ? Okay. If that's the case, then we're good on that. All right, next thing I want you to do is scroll down to store regression equation. Store the regression equation. With your cursor sitting to the right of this store regression equation, I want you to hit your vars key, V-A-R-S. Your vars or your variables key is above your TAN button, T-A-N. Vars. And then, ladies and gentlemen, I want you to hit your right arrow key to go over to Y-vars. I want you to stay on function and then hit enter. And then I want you to hit Y1, select Y1, your cursor sitting there, hit enter. You should see Y1 pop up from whence you came. Does it now show back in your linear reg screen as Y1 here? Anybody's that doesn't show this? Go down to calculate. Ladies and gentlemen, we're about to perform linear regression on this bivariate or ordered pair data set. Hit enter. Regression has been performed. You know what your linear regression equation is that fits those 10 data points? It would be y is equal to 0.2685 times x plus your y-intercept, which is 11.113468283. That's your y-intercept. I don't know. Did anybody get that? Anybody follow me?
Yeah.
Okay.
Yeah.
We got something there. So what I'm gonna do is we gotta round off these decimals somewhere here, ladies and gentlemen. Look at these decimals ramble on forever for the slope and the y-intercept here. I think your author wanted us to round them off to 1 decimal place. And so, ladies and gentlemen, the linear regression equation or least squares regression equation that fits these data points the best, the tightest, if you will be 0.3 x plus, they wanted 1 decimal place, right? So 11.1. So this, ladies and gentlemen, this equation is called your linear regression equation. Linear regression equation. All right, linear regression equation. Notice we have modeled the age of the puppy versus the weight of the puppy according to a linear model here. X is the weight of the puppy, excuse me, the age of the puppy days after adoption. That's what X is. Y is the weight of the puppy in pounds, okay? Notice what's happening to the weight of the puppy, ladies and gentlemen, every day after adoption. Is it increasing or decreasing?
Increasing.
It's increasing by what rate? At what rate?
30%.
Yeah, or 0.3 pounds or 0.3 of a pound per what day? That's the increase in weight that the puppy's experiencing every day, the rate of increase in its weight, 0.3 pounds per day. 11.1 pounds was the weight during day 1 when the child first adopted the puppy from the shelter. The weight was 11.1 pounds. That's what the y-intercept represents, the initial weight, okay? All right, let's go back to our calculator. Ladies and gentlemen, not only have we performed regression, but we told our calculator to store our regression equation in Y1. Wasn't that the case? So if you hit your Y equation editing mode, hit Y equals. If you hit Y equals, guess what you see? There's your regression equation. We told your calculator not only to compute, but also to store in Y1. Remember that? We told it to store it in Y1. All right. Now, ladies and gentlemen, I want you to go to Zoom. Hit Zoom. Go down to Zoom Stat. Zoom Stat. Hit enter. You will see not only the 10 data points plotted, you're going to see the overlay of the regression equation graphed. Look at how tight that regression equation fits these data points. We would say that this is a very accurate linear model, ladies and gentlemen, to try to model the weight of this puppy versus its age after adoption. Okay. Did anybody get this far where they're actually seeing the graph that I see?
Yeah.
If you missed any of this, ladies and gentlemen, example 8 on page what? Well, in section 2.5, example 8 goes over this in detail, showing you the key steps on the calculator and everything. So please look at example 8 in section 2.5 if you missed this routine. Regression, simple regression analysis is what we just conducted here, okay? All right. Suppose I went out in the field, ladies and gentlemen, and I collected an ordered pair data set, and suppose I made a scatter plot of those ordered pair data points I collected. What if the scatter plot looked like this? Do you think problem number 67 would be a problem where we might want to apply linear regression to model this data? Yes or no? Do you think this data is a good candidate for linear regression, ladies and gentlemen? Does it appear that these data points lie on a line, roughly?
Yeah.
Yes, this would be a good candidate for linear regression. Ladies and gentlemen, suppose I went out in the field and collected an ordered pair data set and then came in and plotted the data points in the XY plane. Suppose its scatter plot or graph looked like this. Would this data set be a good candidate for linear regression? Does it appear these points lie on a line?
No.
No. Ladies and gentlemen, we would have to use a different sort of a regression to try to model this data set. We might have to use what's called a quadratic linear regression, quadratic regression, not quadratic linear regression. We might have to try to fit a parabola to this data. Do you agree? Instead of a line. That's called quadratic regression, right? We're not going to study nonlinear regression in here. All we're studying is just linear regression. So it looks like 67 and 68's data set would definitely warrant that we would conduct linear regression to try to model it. But 69 and 70 look like we would have to use some sort of a nonlinear regression to try to model these curve type constructs with these points. Okay. All right. Okay. The only classwork I want you to do today, ladies and gentlemen, there's one problem. It's number 59 on page 224. Let me go to that problem. Problem 59. There it is, ladies and gentlemen, number 59 on page 224. This is your classwork problem for today. Let's see if you can do some of this, all right, in the time remaining. Go ahead. Classwork, your only classwork is this problem. 59, page 224. See if you can answer these questions. Here's a hint. Let X be equal to the number of dozen cookies that are produced and sold. X equals the number of dozens that are produced and sold. All right. Let's take a look at these. 59A, ladies and gentlemen. Did you get that for the cost function? If X is equal to the number of dozen of cookies manufactured and sold, do you agree this would be our cost function? Did we get that? Did anybody get this?
Yes,
Somebody did, all right. Cost 24 cents. It cost us 24 cents to make one dozen cookie, 1 dozen of cookies. We have a fixed cost of $790 every month, just to rent the joint and other fixed costs. We are going to charge $6 per dozen. If we sell X dozen, we will rake in this amount of revenue, agree? The profit function is revenue minus cost after cleaning it up. Did anybody get this for the profit function of selling X dozen cookies?
yes,
This is the profit function. Ladies and gentlemen, I want to know at least how many dozen must you sell in order to start making a profit? You can do this problem mathematically if you just insist that your profit function be greater than 0. If you insist your profit be greater than 0, that means you're going to start making money. So why not set your profit function greater than 0, solve the inequality for X, and I came out with the fact that you better process more than 137. Actually, it should be more than 138 dozen, ladies and gentlemen. You better sell more than 138 dozen. Well, 138 dozen or more. You better sell of cookies in order to start making a profit. Okay. If we sell 150 dozen cookies, will we make a profit? And if so, how much? The answer is evaluate your profit function at 150. You'll make $74 profit. Did anybody get that? Anybody get these answers or not? All right, somebody's trying to talk, but I can't hear. Did anybody get these answers? Somebody did? All right. Now, another way of determining you have to sell at least 138 dozen is you could use your break even. You could use your graphing calculator. And then, the left side could be the graph of the revenue function, the right side, the graph of the cost function. Look for the break even point, and you'll see that you're going to have to sell at least 138 dozen cookies, ladies and gentlemen, to break even, to be above the break even point, if you will, where your revenue starts to exceed your cost. Okay. All righty. All right. So that is the only classwork that I would like you to turn in by midnight tonight, ladies and gentlemen. And I did update Alex as far as the homework is concerned. I think I'm updated on the textbook homework, although I think in 2.4 is it? I think in
Yeah, that 2.4 is not on there yet.
one of the sections, I don't think I assigned any textbook homework problems. I will have to, pull a couple of those out of your textbook and give you that for an assignment. But I think Alex will keep you busy for the time being. Okay. All right. If there's no other questions, you guys have a great weekend, ladies. I'm going a safe weekend, and hopefully I'll see you next week. And try to stay up with the homework seriously. Try not to get behind. I mean, it's really a waste of time if you let it all go until the very end, because you're not really nurturing your mind on a daily basis. You want to try to, kind of stay in sync with what it is I'm talking about. Please do look over some of the examples in this section that I covered. That's an awesome way to solidify what I've discussed here today, is by going over some of the examples your author shows you in your textbook. All right. Have a good day. I will stay on the line for a couple minutes, but I would really like to end this so I can start converting this video into the MP4 format, ladies and gentlemen, as it takes forever on my computer. So if there's no other questions, I would like to sign off here pretty soon.
How do I get, so on my calculator,
Uh-huh.
when I hit graph, it still has like the plotting points that we did, like for that one problem.
Yeah. Okay. Here's
How do I
what you
get
can
rid of
do. If you don't want to see those anymore, you can do this one of two ways. You can hit your Y equals button here.
Okay. Okay,
And notice my stat plot one's still turned on here. You see that?
okay,
Just move your cursor up onto plot one's name and then hit the enter button. That will toggle the plot to the
Oh.
off position. You see that?
yeah,
It's
I
now
got it.
turned off, okay?
All right,
Yep, that'll
Thank you.
work. Mhm. All right, any other questions or concerns here?